Welcome to the lesson for the RM10 assignment, Simple Mole Conversions. Today we're going to start by talking about molecular mass. All masses on the periodic table are given in grams per mole. But what is a mole, you ask? The mole. The mole is just a word that represents a number, just like pair represents two. So when I say there are a pair of shoes, there are two shoes. And when I say a dozen, I mean 12. And when I say I have a dozen eggs, I have 12 eggs. Just like when I say I have a mole of atoms, that means I have 6.02 times 10 to the 23 atoms. As you may have heard, atoms are very small, and individually they are quite insignificant. If we were to conduct experiments based on individual atoms, all our values from mass to energy would be extremely small and also quite insignificant. These are the steps towards how the mole was derived. The gram had been established and accepted many years prior. All life is based on carbon, carbon-12 being the most abundant isotope of carbon. Carbon-12 is 6 neutrons and 6 protons, significantly contributing to its mass. Scientists decide that carbon-12 should weigh exactly 12 grams. Scientists determine that 12 grams of carbon-12 contain, through experimentation, 6.02 times 10 to the 23 atoms of carbon-12. Scientists agree to call the number 6.02 times 10 to the 23 a mole, and most importantly, in order to save time when writing mole, the abbreviation MOL is used for mole. When we deal with chemical equations, we find formulas for molecules and individual atoms. Since these are so small, we often talk in terms of moles of atoms and moles of molecules. Since we know that a mole is a word that represents the number 6.02 times 10 to the 23, it stands that 1 mole of molecules equals 6.02 times 10 to the 23 molecules, and that 1 mole of atoms represents 6.02 times 10 to the 23 atoms. So 1 mole equals 6.02 times 10 to the 23. And that's known as Avogadro's number. Now, note that this is on your pink sheet. And that's going to allow us to do conversions. Because remember, when we did conversions before, inside brackets, we make sure that the top equals the bottom. We know that 1 mole equals 6.02 times 10 to the 23 molecules or atoms. So that means this is going to allow us to convert between moles and molecules or atoms. So we can now do conversions between molecules and atoms and moles using the number 6.02 times 10 to the 23. Now, when you go to put Avogadro's number into your calculator, you punch in 6.02 second function, so you can get that EE, and then you press 23. Now remember, when you hit second function EE, that E appears on your calculator face. You can sub in the words times 10 to the for the E. So when I read 6.02 E23, that means 6.02 times 10 to the 23. Now, the error that a lot of grade 11 students make, they write 6.02 times 10 to the E23, which is then 6.02 times 10 to the 23, which is actually 6.02 times 10 to the 24. And that's why, when you check the answer key, a lot of students wind up with the right number at the front, but when they get to the times 10 to the, they're always off by one number. So this is not what we do. Molecular mass. All masses on the periodic table are given in grams per mole. That is how much 6.02 times 10 to the 23 atoms of that element would weigh. If I look up carbon, it says 12.011. That is how much 6.02 times 10 to the 23 atoms of carbon would weigh in grams. Now, why not 12 exactly? That's because in nature, 98.9% of the carbon weighs 12 atomic mass units, and 1.1% weighs 13 atomic mass units because its nucleus has one more neutron in it than carbon-12. And there is also carbon-14 that could be found, but it is very rare in nature. The mass of 12.011 then works out to be the average mass of a carbon atom in atomic mass units. If I look up aluminum, it says the mass of aluminum is 26.981539 grams. That is how many grams are in 1 mole, or 6.02 times 10 to the 23 atoms of aluminum. Same thing with oxygen. 6.02 times 10 to the 23 atoms of oxygen weigh 15.9994 grams. The mass of a chemical formula is then calculated by adding the mass of all the elements in the formula together. The chemist then has the mass of that formula in grams per mole. So if we want to find the weight of aluminum oxide, first thing I do is look up aluminum on the periodic table and I write down the mass of aluminum twice. I look up oxygen. I have 3 oxygen atoms, so I write down the mass of oxygen 3 times. I add them up, and then I correct for significant figures, and then I write my answer. In this case, I don't usually round the masses. It is very rare to calculate the mass and not use it in a future calculation. And being that I cannot round till I get to my final answer, I like to keep my pre-rounded answer. I just make sure that I identify which digits were not significant. Now for a quicker way to add those masses up, I look up barium and write down its mass. I write down oxygen, write down its mass and multiply it by 2 because I have 2 oxygens. I look up hydrogen, write down its mass, multiply it by 2. Then I just punch it into my calculator. 137.327 plus 2 times 15.9994 plus 2 times 1.00794, and that gives me 171.34168. And when we correct for significant figures, since it was all adding, we just look at how many decimal places the elements were good to significant figure-wise. Barium was good to 3 decimal places, oxygen to 4, hydrogen to 5 decimal places. That means barium had the least precision in its measurement, being only good to 3 decimal places. So therefore my answer is only good to 3 decimal places. So I underline the 6/8 and I'm good to move on. Now that we can calculate the number of grams a mole of substance weighs, we are able to convert from moles to grams and vice versa using dimensional analysis. This will be often used since most calculations in chemistry are based on the mole, but all measurements of weights are in grams. Locate on the pink sheet where it says 1 mole equals blank amount of grams. Now why blank? It's because the mass is going to depend on what elements are inside of the formula. So every time we do a question, we are going to have to add up the masses. That will go into the blank with grams, and it will equal 1 mole of that formula. So now we can convert between grams and moles. So we can now do conversions between grams and moles using the masses off the periodic table. Gases occupy a specific amount of space based on the pressure and temperature of the gas. The conversions between volume and moles of gas are usually done under one of 2 conditions. STP, standard temperature and pressure, at 0 degrees Celsius and 1 atmosphere of pressure, 1 mole of gas occupies 22.4 liters of space. Make a note that STP is 0 degrees Celsius on your pink sheet. Now 0 degrees is quite cold, so we also use RTP, room temperature and pressure, also known as NTP, normal temperature and pressure. At 25 degrees Celsius and 1 atmosphere of pressure, 1 mole of gas occupies 24.4 liters of space. Hot air expands. If we go from 0 degrees Celsius to 25 degrees Celsius, the gas is warmed, it is expanded, it occupies more space. Make a note on your pink sheet that RTP, NTP is 25 degrees Celsius. Now, we can do conversions between liters and moles using these two values. Just as we use things like 10 to the negative 2 meters equals 1 centimeters inside of brackets when we did RM9, we are now going to use the following inside of brackets to make conversions involving the mole. Note that all conversions must go through Moletown. So when I'm working through the assignment, what does that mean? If not given moles, our first conversion must always have to be 2 moles. Example 1, how much do 8.00 moles of gold weigh? First thing, as always, write down my given, put in some big brackets. I have moles AU. I'm going to want to get rid of moles AU, so I'm going to put that on the bottom so they can factor out. Now I got to figure out where am I going to from here. Well, I have moles and I want to find out how much this weighs. So that means I'm looking for a mole gram conversion. So I have to get the mass off the periodic table. I look up gold, I find its mass. So I'm going to go to grams of AU from moles of AU. And that conversion says that 1 mole equals the number of grams on the table. So 1 mole AU equals 196.96654 grams of gold. Moles AU and moles AU will factor out. I'll run it through my calculator. That gives me 1,575.73 grams of gold. Now I need to correct for significant figures. I've got 3 in my given. I've got 8 inside of the brackets. So that means my answer is only allowed to have 3 significant figures. So 1,575.73 grams becomes 1,580 grams of AU. Example 2, how many moles are in 136 grams of strontium chloride? The first thing I do is write down my given, but I have to figure out what the formula is for strontium chloride before I move on. Strontium chloride, it's an ionic compound. Strontium is positive. I look it up on the periodic table. It takes a +2 charge. Chloride is negative. I look it up on the negative list, and it takes a -1 charge. So the lowest common charge is 2. So I have 136 grams of SrCl2. 1 Sr gives me a +2. 2 Cls give me a -2. It balances out. I put in big brackets. I have grams of strontium chloride. I know for sure I'm going to be getting rid of that, so that goes on the bottom. And that is going to be converted into moles. And I know that because the only conversion up at the top that has grams is the one that says 1 mole equals blank amount of grams coming off the periodic table. So we're going to be switching grams to moles. And it tells us that 1 mole of SrCl2 equals the mass off the periodic table. So I'm going to have to add 1 strontium to 2 chlorines. I punch that into my calculator, 87.62 plus 2 multiplied by 35.4527, and that gives me 158.5254 grams. Note the 54 is underlined, and that's because strontium is only good to 2 decimal places. So if I were to line it up in columns, this answer would only be good to 2 decimal places. Now, grams strontium chloride and grams strontium chloride factor out. I run it through the calculator. That gives me 0.8579 moles SrCl2. Now to correct for significant figures, my given has 3. The brackets have 5. It's all multiplication and division, so my answer is only allowed to have 3 significant figures. So 0.8579 moles becomes 0.858 moles strontium chloride. Example 3. How many molecules are in 213 grams of nitrogen dioxide? First, I have to find the formula for nitrogen dioxide. Looking at the periodic table, I see they are both nonmetals. So that means it is a covalent molecule, and in the naming, they're using covalent prefixes. It just says nitrogen, no covalent prefix, and that's because mono is never used on the first. So I have 1 nitrogen, and then I see dioxide. Di means 2, so 2 oxygen. So my formula is NO2. So we will write down our given. 213 grams of NO2. I put in big brackets, and I know grams NO2 will have to go on the bottom so that grams NO2 and grams NO2 will factor out. I also know I started with grams, so my first move has to be going to moles, because 1 mole equals whatever the grams are off the periodic table. So I'm going to moles of NO2. 1 goes with moles of NO2, but I have to find the mass in grams for NO2. And to do that, I go to the periodic table and I add 1 nitrogen to 2 oxygens. So 14.00674 plus 2 multiplied by 15.9994 gives me 46.00554. I underline the 4 because it is not significant, because oxygen was only good to 4 decimal places. So when I added those masses together, it is only good to 4 decimal places. Now I'm going to put in another set of brackets, and I currently have moles of NO2. That is not what I want in the end. It says how many molecules. So I will put moles of NO2 on the bottom, and I'm going to put molecules NO2 on the top. I'm using the conversion 1 mole equals 6.02 times 10 to the 23 molecules. So 1 mole equals 6.02 times 10 to the 23 molecules. Now, when we enter 6.02 times 10 to the 23 in our calculator, remember we punch in 6.02, second function EE, 23. Now, moles NO2 and moles NO2 will factor out, and I'll run it through my calculator, and I get 2.787 times 10 to the 24 molecules NO2. My given has 3 significant figures. My first bracket has 6 significant figures, and my second bracket has 3 significant figures. So my answer is only allowed to have 3 significant figures. So it becomes 2.79 times 10 to the 24 molecules NO2. What volume does 13 grams of nitrogen dioxide occupy at STP? First thing I do, write down my given, put in some big brackets. I have grams NO2, so I will want to get rid of grams of NO2, so I will put it on the bottom, and I'm going to convert that to moles. And I know it's going to be converted to moles because we weren't given moles to begin with, and all conversions have to happen through moles. So if I'm not given moles at the very beginning, my first conversion is always switching it to moles. Now, what numbers do I put in there? Again, here's the line with moles and grams. 1 mole weighs the grams that are on the periodic table. So 1 nitrogen added to 2 oxygens, and that gives us 46.00554. I didn't calculate it this time. I used it from the previous example. Now, in the assignment, there are situations where you will have the same formula over and over again. I suggest on the quiz and on the assignment, make sure you always double punch the mass. Because if you've made a mistake and then you recycle that same mass, as you work your way through the assignment, those questions will all be wrong. So always punch the mass in, write it down, and then punch it in a second time to confirm you didn't make any mistakes. So grams of NO2 and grams of NO2 will factor out. I now have moles of NO2, but it says what volume? And volume is not measured in moles. Volume is measured in liters. So I know I will need another bracket. And in that bracket, now I want to get rid of moles of NO2, so I'll put moles of NO2 on the bottom. And if I'm going to volume, I want to switch it to liters of NO2. And the line I'm going to use is this one, because I was told STP. And this line has 1 mole equals 22.4 liters. So 1 mole equals 22.4 liters. Moles NO2 will factor out. I run that through my calculator. 13 multiplied by 1 divided by 46.00554 multiplied by 22.4 divided by 1 gives me 6.32967 liters of NO2. Now to correct for significant figures, 2 in my given, 6 in my first bracket, 3 in my second bracket. So that means my answer is only allowed to have 2 significant figures. So my final answer is 6.3 liters of NO2. Example 5, how many moles of hydrogen gas are present if a sample at RTP occupies 126.8 liters? So we've got hydrogen gas to begin with. Gas that's its state really doesn't matter to us, but we want to find the formula. If I look on the periodic table, I have highlighted the hydrogen, and that's because it is a diatomic. So when I talk about just hydrogen, I write H2. So I have 126.8 liters of H2. Big brackets, I currently have liters of H2, and I'm going to be going to moles because, again, if I'm not given moles to begin with, my first step is always converting to moles. So I'll put liters of hydrogen in the bottom so they can factor out, and I'm going to moles of H2. Now I'm looking at which conversion am I using, and it's going to be one of the top two. 1 mole equals 22.4 liters, or 1 mole equals 24.4 liters, and that all depends on what was given to me in the question. And it says the sample is at RTP. So if it's at RTP, I'm using 1 mole equals 24.4 liters. So 1 mole equals 24.4 liters. Liters H2 and liters H2 will factor out. I was asked to find moles. I currently have moles, so that means I'm done. So I'll run it through my calculator, and I get 5.1967 moles of H2. Correcting for significant figures, my given has 4, my brackets have 3, so that means my answer is only allowed to have 3 significant figures, so 5.19 gets rounded up to 5.20 moles of H2. And that brings us to the end of the lesson. Get to work on that RM10 assignment.